If we have 2 points P and Q, then there are many ways we can draw a circle through those 2 points. Here is just one example. If we have a third point R, is it now possible to draw a circle through all 3 points? Well, even if we only restrict ourselves to the circles through P and Q, where the centre is the same distance from both P and Q, this is going to be possible. We can consider all such circles, and when it gets to the point where that circle passes through R, we can stop. Here is a circle that passes through all 3 points. This situation is usually described by starting with the triangle that has P, Q and R as its vertices, and talking about the circle that passes through all of the vertices of the triangle. This circle is called the circumcircle of the triangle, and the centre of that circle is called the circumcentre of the triangle. So we have these definitions. For a given triangle, the circle passing through the vertices of the triangle is called the circumcircle of the triangle. The centre of this circle is called the circumcentre of the triangle. So to illustrate again, starting with this triangle, the circle which passes through all 3 vertices is the circumcircle of that triangle, and the centre of that circle is the circumcentre of the triangle. It is interesting to note that the circumcentre of the triangle may be inside the triangle, as in this case, or outside it, as in this position. But in any case, we can always find a circle through the vertices of the triangle. The next question we have to address is how to do this. Well, we know that the perpendicular bisector of a chord of a circle passes through its centre. So if we find the perpendicular bisector of the chord PQ of the circle, that will pass through the centre of the circle. Similarly, the perpendicular bisector of the chord PR will pass through the circle. So if we can find the equations of those 2 perpendicular bisectors, their point of intersection will be the centre of the circle. Of course, this will also be true of the perpendicular bisector of the chord RQ, but we will only need to find 2 of those perpendicular bisectors to find where they intersect. Having found the centre of the circle, we can now consider the straight line segments joining the centre to the vertices of the triangle. These are all radii of the circle, so if we just find the length of any one of them, we have found the radius of the circle, from where we can deduce the equation of the circle. So we have a formal method to find the circumcircle of a triangle. Firstly, we can find the equation of the perpendicular bisector of one side of the triangle. Then we can find the equation of the perpendicular bisector of another side of the triangle. We find the point where these perpendicular bisectors intersect, and that will be the centre of the circle. We find the distance between the centre of the circle and any of the vertices of the triangle. This will be the radius of the circle. Now that we know the coordinates of the centre of the circle and the radius of the circle, we can write down the equation of the circle. Let's put this into practice. The points A, B and C have coordinates -2, -4, 5, 3 and 5, -5 respectively. Find the equation of the circumcircle of the triangle ABC. We have this triangle, and we are trying to find the equation of the circle that passes through the vertices. Let's begin by considering the perpendicular bisector of the chord BC. In this case, there's no need to go through a large formal method to find the equation of this perpendicular bisector. We can see that the points B and C lie on the same vertical line with equation x equals 5. Therefore, the perpendicular bisector is a horizontal line with the equation y equals some constant. All we need to do is find the y-coordinate of a point on that line, and the midpoint of B and C is the obvious example to use. B has a y-coordinate of 3, C has a y-coordinate of -5, exactly halfway between those is -1. So the equation of this perpendicular bisector is y equals -1. Now we'll consider the perpendicular bisector of the chord AB. This will require a little more work. So what is the gradient of the chord joining A and B, using their coordinates, it will be the difference in the y coordinates, -4 subtract 3, divided by the difference in the x coordinates, -2 subtract 5, which is -7, divided by -7. That gradient is 1. Therefore, the gradient of the perpendicular bisector will be -1 divided by 1, which is -1. We are also going to need to know a point on this line, and the midpoint of A and B is the point to use. What are the coordinates of that midpoint? We will have to average the x coordinates of A and B and the y coordinates of A and B. That midpoint has coordinates 3/2, -1/2. Therefore, the equation of the perpendicular bisector is y subtract -1/2, y plus 1/2 is equal to -1 times x subtract 3/2. So we have that y plus 1/2 is -x plus 3/2. Subtracting the half from each side, we have that y is -x plus 1. So now we have the equations of the perpendicular bisectors of two sides of that triangle, and we know that they are going to intersect at the centre of the circle. Let's work out the coordinates of that centre. Well, we have just calculated this equation for one of those perpendicular bisectors, but earlier on we realized that another has equation y is -1, so solving these simultaneously, we have that -x plus 1 is -1. In other words, -x is -2, so therefore x is 2, and the centre of the circle has coordinates 2, -1. We now need to find the radius of the circle, which will be the distance between the centre and any one of the three vertices. It makes no difference which one we choose. Let's use B. So B has coordinates 5, 3. The distance between the centre and B, the radius of the circle, will be 5 subtract 2 squared plus 3 subtract -1, same as 3 plus 1 squared, rooted, which is the square root of 3 squared plus 4 squared, which is the square root of 9 plus 16, the square root of 25, that radius is 5. Therefore, we can say that the equation of the circle is x subtract 2 squared plus y subtract -1, or y plus 1 squared, is equal to 5 squared. An interesting situation is when we are looking at the circumcircle of a right-angled triangle. Here we have a right-angled triangle PQR. So if we look at the perpendicular bisector of PQ, because vertically the hypotenuse of this triangle has its lowest point on the same level as P and its highest point on the same level as Q, then this perpendicular bisector is not only going to cut PQ in half, it's also going to cut RQ in half. A similar argument will apply to the perpendicular bisector of PR. Horizontally, the hypotenuse of the right-angled triangle ranges from the position of P to the position of R, so this perpendicular bisector is also going to cut it exactly in half. We know that the centre of the circle is where these two perpendicular bisectors intersect, so we have the following result. The circumcircle of a right-angled triangle has its centre at the midpoint of the hypotenuse of that triangle. A consequence of that is that the hypotenuse of the right-angled triangle is a diameter of the circle. It is possible to deduce a similar result in reverse, in that if we have a straight line which is a diameter of a circle, and then we form a triangle with any other point on the circumference of the circle, then the angle at that point will always be a right angle. Wherever I move this third point to, the angle at that point will always be 90 degrees. We have these results. The circumcircle of a right-angled triangle has its centre at the midpoint of the hypotenuse of the triangle. But it is a second form which is more widely used. The angle in a semicircle is a right angle. That is an expression of this idea. When we have a diameter of the circle and another point on the circumference forming a triangle, then that will always be a right-angled triangle with the right angle at the point which is not on the diameter. We can sometimes use this idea as an alternative approach to circumcircle questions. The points A, B and C have coordinates -4, -4, -6, 10 and 10, -2 respectively. Find the equation of the circumcircle of the triangle ABC. Let's work out some distances. In fact, it will be even nicer for us to work out the squares of some distances. So how far is it from A to B squared? That will be the difference in the x-coordinates of A and B, -4 subtract -6 squared, plus the difference in their y-coordinates, -4 subtract 10 squared, which comes to 200. What's the distance from B to C squared? That is -6 subtract 10 squared plus 10 subtract -2 squared, which is 400. How far is it from C to A squared? That is 10 subtract -4 squared plus -2 subtract -4 squared, which is also 200. We can see that the distance from A to B squared plus the distance from C to A squared is the distance from B to C squared. Therefore, the lengths of the sides of that triangle satisfy Pythagoras' theorem, and therefore it is a right-angled triangle. Let's illustrate this situation. Because we know that we have a right-angled triangle, we know that the centre of the circle will be the midpoint of the diameter BC. So this midpoint will have coordinates which are the average of the coordinates of B and C. Those coordinates are easily seen to be 2, 4. Since we have already done a calculation to find the length of BC, we also know the radius of the circle because it is half of that length. So to recap, we know that the centre of this circle has coordinates 2, 4. We know that the hypotenuse BC has a length squared which is 400. That means that the length BC itself, being the square root of 400, is 20, and that means that the radius of the circle, being half of that length of the diameter, is 10. So we can write down the equation of the circle as x subtract 2 squared plus y subtract 4 squared is 10 squared. This is not a technique that you would use unless you had some reasonable suspicion that the triangle involved is right-angled. Otherwise, you may just spend a long time working out these three lengths for no particular reason. However, if there is any clue in a question that you may be dealing with a right-angled triangle, this method is substantially quicker than the previous one we have seen.